Hi, this is Jose Luis, and welcome to another video in this series, Introduction to Parametric Modeling. Now, we have seen in the previous videos a lot of geometry types, numerical series, vectors, blah, 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 whatever, a lot of stuff to create geometry, mostly. However, we have not really seen any tools or any ways of manipulating, changing, or transforming geometry. So what we're going to learn in this video is the different ways we have to perform transformations on existing geometry. And transformations is just the technical word that, if you will, that we typically use to refer to simple operations that change the shape or the location of an object in three-dimensional coordinate space. Like, for example, those can be translation, which is also a technical term for moving things around. That can be rotation around different references, axes, points, planes, or etc. It can be scaling, which can be making an object larger or smaller uniformly in every direction or non-uniformly, just in one direction. That can be, we can have reorientation, which is when you change an object from one reference plane to another reference plane. And there's actually multitude more. There's shears, there's projections, there's morphings. There's actually a lot of different transformations that we can apply to geometry. So in this video, I would like to teach you the basics of how to perform transformations in existing geometry. And at the same time, I would like to teach you also a little bit on the underlying mathematics, just a tiny bit of what's going on under the hood, so that you understand so that this paves the way for you to understand in more advanced topics of how transformations are represented numerically, aka with a 4x4 matrix. But that's something that we're not really going to look at in this video yet. We're still beginning. So let's take a look at how we can perform transformations, for example, in Grasshopper for Rhino. So we are here in Rhino, and I have this banner that I just created a few minutes ago, where I just added some text. On Rhino, I wrote pcamp with the typeface that we use here in the channel. I then exploded the typeface and extruded it into solids, making these 3D kind of letters that I'm going to be using for transformations. And actually, just to make things easier, I'm just going to use one of them. I'm just going to use the P in the transformation. So I'm going to take the extrusion and I'm going to copy it and I'm going to bring it somewhere here in the middle of nowhere, okay? So that I can just practice with it. And you can see that this object, I extruded it in a solid way, which basically means it's kind of watertight. And it turns out that different modeling environments have different ways of handling solids. In this case, for example, the way Rhino works with solids is that there aren't really solids as an entity, whereas the way Rhino works with them is just by grouping a bunch of surfaces that delimit the boundaries of this solid object into an object that is typically called a B-rep or a boundary representation. So Rhino calls them solids, whereas here in Grasshopper they're typically called B-reps. So if I go to geometry, and you can see that I have B-rep, which stands for boundary representation. So I'm going to drop an empty B-rep component and some bifocals for those of you non-icon people still. Okay, it's okay. So I'm going to drop here a B-rep component, and then I'm going to right-click, set one B-rep, and set this object so that all the surfaces are grouped into this more complex object called a B-rep, right? And then what I'm going to do is I'm going to start now manipulating this B-rep, moving it, scaling it, and doing like a bunch of things to it. Most of the transformations that are available inside of Grasshopper can be found here under the Transform tab. So if I click on the tab, you can see that there's a few different groups or categories of transformations. Perhaps the most common ones are under Euclidean transformations, like for example, mirroring, moving, oriented, rotating. And some of the most useful ones are also here under scaling, shearing, scaling not uniform, and projecting. We're going to see a few of those here. And the first one that I would like to start with, well, There's another category called morphing. These are a bit more esoteric, and they relate to the nerves nature of a lot of the geometry that is found in Rhino. But they're a little more complex. I don't think we're going to see any of this here in this introductory series. So I'm going to go to Euclidean, and I'm going to start working with the simplest one, which is going to be moving, or translating, the more technical term. I'm going to place the move component here, and I'm going to zoom in, and I'm going to see that what the move component is asking me is for any base geometry. And you can see that the hexagon icon has this like sort of like spiral, whatever that is. And it means that when it comes to this, it means that this is a collection of generic geometry. What's interesting is that transformation components, most of them can transform any geometry. They can transform planes, vectors, they can transform points, they can transform curves, surfaces, B-reps, meshes. So that's why instead of giving us a hard type that we need to use, it gives us the generic base geometry input. And then the other input that it asks for is a translation vector. So it is, if we want to move, we're going to have to move in a particular direction. So that's why in this case, vectors make a lot of sense as the input for this transformation. So what we're going to do is I'm going to plug here the geometry that I want to move. And what I'm going to do now is I'm going to create a vector from components that I just did offline. So I have a vector that I'm constructing with 3 sliders, and I'm going to plug this vector into the move component. What you can see is that my original vrep, which is this one, now has been moved by 1 unit in the x direction or more, right? Let me move this here a little bit, or 1 or more. Then, or I can just move it in the y direction, or I can move it in the z direction, or both. I can move it in the 3 particular angles. So moving is just as simple as having the input geometry that we want and the translation vector indicating the direction and the magnitude of how much do we want to move an object. Another very simple operation that we can perform, another very simple transformation is, for example, scaling an object, right? So I can go to transforms and I can go to affine transformations and look for scaling, which in this case, this one scales the object uniformly in all directions. So for example, I can take this, I'm going to hide this one, and then I'm going to, I'm going to move all of this here, and then I'm going to look at the inputs. G is going to be the geometry I want to scale. C is going to be the center of scaling, because scaling actually needs a center point of reference for the scaling, and the factor. So, okay, so I'm going to plug in here the B-rep, and then for the center, I'm going to use an actual point that I'm going to bring into Rhino. So for example, I'm going to use this point here. I'm going to bring it into Grasshopper. So right click, I'm going to set this point. So this is going to be the center of scaling. And you can see that apparently there's already like in the scaling factor, there's a 0.5 default value. So I'm going to add another slider, which is going to be the factor. And you can see that I have now scaled my P by a factor of 10 from that reference point. And if I move the reference point, you can see that the scaling is going to get some kind of offset, because the point of reference is very important as the center of the scaling operation. Scaling, so I could, for example, scale this from the center of the base. I guess I could scale this from the center of the P. And if I do 0 less than 1, you can see that I'm actually reducing the size of the P. Okay? So I'm going to now move this outside, or I'm going to keep it at the base. Okay? So this is scaling uniform, but there's also scaling non-uniform. So this one here, scaling non-uniform, an object with non-uniform factors. If I drop this here, you can see that it's a little more complex. It takes a base geometry, it takes a plane for the non-scaling, for the non-uniform scaling, because it needs the 3 directions. The 3 directions are important now because it's not an uniform scaling. And then x is going to give us the scale factor in x, y, and z. So for example, what I can do, I'm going to turn this one off. I'm going to use the point as the center for an xy plane. So I'm going to drop here, I'm going to drop here an xy canonical plane. All right, I'm going to use this point as the center for this plane. So now you know that you see that the plane is here and is oriented in xy. And I'm going to use that plane as the center for as the reference for my non-uniform scaling. I'm also going to bring here the object, and you can see that x, y, and z right now are 1, 1, 1. So let me drop here 3 components, all right? And that's going to be x, y, and z. And you can see that right now they're uniform. But for example, I can squish in the x direction, make it very large in the y direction, and kind of stretch it up and down in the z direction. So that is because the scaling is now different in each one of the directions. If I change the plane and the plane had a different orientation, then the scaling would be different right now in each direction. You see? Okie dokie. So what is next? Well, you might be asking yourself for this particular exercise in the case of the uniform, if the uniform scaling. In the case of the previous one, the uniform, how can we, for example, let me turn this on. How if we had here a manual point, right? That we moved around. But how could I make sure, for example, that I always scale a particular B-rep around its center? How could I do that instead of just manually moving the point around? Well, that would be as simple as an operation where we just need to find, for this particular B-rep, we just need to find its center, its centroid. And how can we do that? Well, we can actually do that with components. So for example, if I go here to surface and I go to analysis, you can see that here there is a component that calculates the properties, the volume properties for closed B-reps and meshes. And if I drop that component here, you can see that for that geometry, B-reps or meshes, it gives me the volume numerically, but it also gives me the centroid of the geometry as a point. So what I can do is I can plug this in here, and you can see that this component actually takes some calculation. It's not a cheap one. And the volume of the P is like 0.3 something something, and the centroid is this point that has shown up here. Okay, so if I now plug in this centroid here, you can see that I'm now always scaling uniformly on the center of the B-rep, which is also kind of interesting. So I can choose a reference point, or I can choose a parametrically defined center of gravity for this particular B-rep. What is the next thing we're going to see? Well, I think rotating is a good one that we can take a look at. For example, so if you take a look in transformations and Euclidean, you can see that there's like 4 different types of rotations. Each one of them, the only difference is what kind of information do they take, whether if it's rotating around the plane, rotating around an axis, rotating around a line as an axis, or having 2 vectors and then rotating from one to the other, kind of like, so respecting the 2 orientations. I don't have a particular preference. I kind of do. I like rotating objects on a plane because I typically work with planes a lot, and because planes embed a lot of the information that is useful for rotating things, like the center and like a particular rotation axis. It's a really interesting structure. So let's take a look at that. So rotate is going to take base geometry, the rotation angle in radians, and a rotation plane. So for example, I'm going to take this B-rep and I'm going to plug it in here. The rotation angle is going to be whatever. I'll set that up. And the rotation plane is going to be the same plane that I created before. It's going to be this plane that is rotated, that is oriented in X and Y, and it has the center at this point that I can move around. Okay, so let me turn off scaling. And then what we're going to see is that as soon as I plug this here on the plane, because the default value here is rotation angle in radians, then it rotates 90 degrees. Because if you remember, a full turn in radians is 2 pi radians. So half pi radians is 90 degrees, which I know it's very confusing, and that's why I am a Taoist instead of a Piist, which I haven't bothered you with that yet, but if you Google Tao Day and my name, you will find probably like some stuff on the internet about me and advocating for alternative mathematical constants. Anyway, we'll talk about that some other time. Nevertheless, so what I'm going to do is I'm going to place here a slider that is going to go from 0 to 360 in with, for example, 2 decimals. Okay? And then what I'm going to do is I'm going to convert that into radians. So I'm going to take these degrees, convert them to radians, and then plug them in here. What that means is that now you can see that going from 0 all the way to 90, 180, 270, and back to 360. So I can rotate this object. And remember, the plane is very nice because the center also matters a lot. So as you can see, we are rotating around the normal vector of the plane, but the center also is very important because it defines where the object is going to end. So like here, or here, you know. Or if we wanted to rotate the object around its center, the only thing that we need to do is we need to take this centroid, the centroid we calculated before, then create an XY plane, for example, and rotate the object around that plane. So now, for example, I'm going to turn the other plane off. Now you can see that the object is rotating around itself in the world Z direction, because we're using an XY plane. If instead of an XY plane we use, for example, what are we going to use? We used a XZ plane, you're going to see that because the plane is frontal, then the rotation is now going to be like kind of like that. Or if we use, for example, a YZ plane, you could see that the rotation is now going to be around the y-axis. You see? Okay, and then there are other types of rotations, which are basically the same thing, rotating around a particular center of rotation and an axis of rotation, given as vectors and given as a point and as a vector. So basically, this is what the plane contains. So this component is basically taking from the plane the center and the vector and using that for the rotation. So all the other rotations are pretty much the same stuff. It's just that they take different kinds of inputs that you can construct or deconstruct as you wish. And last but not least, as simple examples here, I would like to talk about what I consider one of the MVPs. Like, I love this transformation, I use it all the time, and which is called Reorient, or sometimes called change of basis. The idea behind this transformation, which if I can drop here, is that what it does is it can take any geometry and then given an original initial reference plane and given a target final plane, what the component will do is it will take the geometry and the reference point and the first reference plane, and it will reorient the geometry to match the orientation of the target plane. What does that mean? Okay, so let's take a look at what that is. So I'm going to, it takes geometry and it takes initial plane and target plane. So the geometry is going to be the VREP we've been working with, and I'm going to turn this off. I'm going to turn this, no, I'm going to keep this on. So that's going to be the XY plane that we're going to use for reference, okay? And then this is going to be the original plane that we're going to use for reference. So what I want to do is I want to make sure that I'm going to move this plane, I'm going to reorient this VREP in 3D using this plane as the origin, as the initial reference one. And then what I need to do is I need to create another point, another plane in 3D to remap, to reorient this geometry to. So for that, I have created 3 random points in 3D space that I have brought into that I have brought into Grasshopper here, and that I have brought into Grasshopper here. And then what I'm going to do is I'm going to create a plane. I'm going to create a plane through 3 points. So I'm going to create a plane that has the first point as the origin, the second point is the direction of the x, and the third point is the orientation of the y. So you can see that these 3 points are now creating a plane that has this kind of like rotation in 3D space with the main axis pointing this way and the secondary axis pointing that other way. So if I now use this plane as the target to orient the new geometry, what you're going to see is that this new object shows up here, which maintains a relation with the target plane that is identical to the relation that the original VREP had with the reference initial plane. And if I move these points around, so you can see that the plane is going to rotate, is going to change in orientation, but this P is maintaining that orientation in 3D in reference to this plane, just like the original had that relative orientation with the origin plane. This operation, basically, it's amazing because it encapsulates in one single clean operation. It encapsulates moving, rotating, sometimes scaling. Well, scaling not in Grasshopper because we can't change the size of the planes, but it could in other computational frameworks. And it's like the Swiss Army knife of transformation, if you ask me. It's really, really nice. And also, it's extremely useful because, for example, it's very useful for population or for patterning exercises. So let me show you an example. Let's say we had, let's say this was like a super cool geometry of some kind of window opening or something like that, that we wanted to populate over a surface. So I have created here this surface, and that I'm going to bring into Grasshopper. So I'm going to take that surface, and now I have it loaded here. And then if you remember, what I could do is I could say utilities, and I can subdivide a particular surface on a grid of UV frames, UV planes. And then each one of those planes would have the orientation and the tangency of the surface. We've seen this component in previous examples, so I can subdivide this in X, Y, and for example, this can be, I'm going to be 20 and 20 subdivisions, and this is getting really dense, so I'm going to go to display, plane size, and I'm going to lower this to 0.5 or maybe a little smaller, 0.3, to make sure that I can see these planes. All right, and then what I'm going to do now is I am going to reorient the original. So I'm going to copy the component. I'm going to reorient the original P. The source plane is going to be the same. It's going to be this plane that we created here. But now the target plane are going to be all the frames that we subdivided the surface on. And then as I do that, then ta-da! You can see that, ooh, what happened? Well, it turns out that the surface is flipped and the normals are pointing down. But you can see how all the P's are now, I think this is too many, so let's do 10 and let's do 10 here. And you can see that the P's are now oriented on top of the surface. Can I flip the surface? I'm going to click here and I'm going to flip the surface, and you're right. I can flip the surface, and now the internal orientation is flipped and the normal is pointing up. And you can see how all my P's are very nicely oriented along the tangency of the surface because of the orientation of the planes. All right. So orientation is like a really, really cool operation, and we would not have been able to do this in a different way because we can't really. We had the geometry and we had to reorient the geometry. We couldn't really create the geometry from scratch, in this case using the planes. So this is a really, really useful operation in my opinion. Now, I would like to highlight one very important concept about how we are manipulating the data and how it relates to the visual programming environment in particular. You may not have noticed that most of the operations that I have done, I have basically taken this original brep, which was here in this box, and I have been able to create a second one here that was moved, or a second one that was scaled, or one that was reoriented, or all of these that were oriented on top of the surface, correct? Now, I would like to bring to your attention that in a way, let me just turn everything off and then focus on the main one. In a way, let me just move this away from, yes. So in a way, what we're doing here is not only moving the geometry or scaling the geometry, but in a sense, something what it is implicit in the way we are using the tool in this case, that not only are we, for example, moving this object here to the right hand side, but at the same time, we're also copying it. We are creating a duplicate, a second instance that is the same one, but it's just in a different location in space. Because, because technically when we move the object, we're not really moving the one that we had in the previous component. We're not really moving this brep. This brep stays always the same. Well, because we create a new component with the translation operation, we create a second brep that is somewhere else in 3D space. But we always keep both instances as part of our algorithm, as part of our grasshopper algorithm here, which is the original one and the copy that is somewhere else in space. So that's why, for example, in Grasshopper world, we don't really have a component that is called copy, because copying basically means, for example, moving along a vector that is 0, 0, 0. That could be a copy, like an exact duplicate, right? Whereas very often what we would like to do is we may want to copy a series of breps along, for example, a one-dimensional axis, or create a one-dimensional array. How could we do that? Well, it turns out that it's just as easy as creating a move instruction or a translation instruction, that instead of taking one single vector, it takes a collection of vectors that have been sequenced at a particular interval. And how can we do that? If you remember from the previous video, we could generate those vectors by using numerical series. Let's take a look at how to do that here. For example, let me bring this brep. I'm just going to work all the way below in the definition. So for the sake of not having like a kilometer long wires, I'm just going to copy this brep and move it all. I'm just going to turn this off, and I'm just going to move this all the way down here for to make my life a little easier. Okay, so that I have the brep here. Now, what I would like to do is I would like to create a one-dimensional. I would like to create, for example, 10 copies of this brep that are spaced at an equal distance. So, for example, what I can do is I can go to Euclidean. I can move here, and then I can move my object. But then, what I would like to do is here, as the translation vector, instead of one vector, I would like to generate a series of vectors at regular intervals. The way I can do that is I can, for example, create a numerical series. And if you remember from my previous video, this with series, I can create a numerical series that starts, for example, at 0, that has a step size of 0.75 between values, and it has more or less values, like for example 10. And then what I can do is with this, I can create a set of vectors numerically. So I'm going to construct vectors using XYZ, and I can use the X values to create vectors on with those parameters. So I'm going to copy this, and you can see that the vectors are now vectors that only have X component, and they have 0 for the Y and the Z. So because I have a collection of vectors, now if I move this brep by a list of vectors, the operation is going to be executed with the same vrep for each one of these vectors, and therefore is going to give me a collection of referenced B reps or a collection of all the B reps together. And now you can see that I can spread out the distances. I can decide more or less objects. I can start at a value that is not 0, etc., etc. Okay, but this is the way to create an array, a one-dimensional array of objects, for example, with translations, and implicitly, and this is the most important part, copying them in a way so that I can now I can have a list of the 7 B reps that starting with the original one and then all of them spaced equally in 3D. I would like to highlight one last thing before we move on to practicing all these things, which is that we have taken a look at the components, at all the transformations, and we have seen that they all spit out a G output, which is the geometry that we are transforming. But at the same time, you may have noticed that they all have an alternative output, which is the X output. And the X output for all of them is something called transform. And if you see, if you look at the hexagon icon, is this kind of like spiral arrow, whatever, that basically signifies that what this basically signifies is that for reasons that we're not going to get into this video, but I will point you to further references, any transformation in three-dimensional space can be represented by a matrix of 16 numbers, a 4x4 matrix. And then that matrix of 4x4 numbers encapsulates all the necessary information to perform a particular transformation on a three-dimensional object. What that means is that with those 16 numbers, so for example, moving can be encapsulated as an operation, can be encapsulated as an operation that has 16 numbers. The output of the X component only gives us this literal notation, but if we actually go to transform, and if we go to utilities here, you can see that if you drop a transformation matrix, and I scale it a little bit up, you can see that if I plug this in here, what I get is this 4x4 matrix that is giving me the numbers that I need to perform this operation moving in X for any geometry, any particular object. Similarly here for scaling, this is the literal representation, but if I plug this in here, you can see that scaling is actually, for this particular one, scaling around the center of this point is a bunch of numbers. It's like these 3 diagonals here are changing, these 2 numbers have changed. It's kind of something different, whereas for non-uniform scaling, it's even more complex, I think. Oh, sorry, I need to plug this one here. It's a bit more complex. These 3 numbers change, these 2 numbers change here. For rotation, this is going to be so rotation is going to change. Because we're not rotating anything here. Yes. So rotation, you can see that this 4x4 matrix here changes, and for reorientation is also going to be quite something here. So you see for orientation, because it's the most complex one, basically these 12 numbers here are changing. So what does that mean? We don't really need to know at this level. This is a bit more advanced topics. We don't really need to know why this works and what is the relation between these numbers and the actual transformation. But what this is useful for is for understanding that a particular transformation, moving, rotating, scaling, can be represented with these 16 numbers. And once a component generates these 16 numbers, then what's very interesting is that those numbers, those matrices, can then be used and applied to any other geometry right off the bat without having to generate that matrix again. So let me show you an example. This component has generated 7 matrices for moving in 7 different steps. So what I can do now is I can say, let's say that I wanted to perform the exact same transformation to a different letter. So I'm going to take, for example, the C, and I'm going to copy it, and I'm going to, oh, where am I here? I'm going to copy it and I'm going to put it somewhere here. All right. What I could do now is I could say, let me bring the new geometry as a brep. I'm going to import it here. And now I have it here. And then what I would like to do now is I would like to move it with the exact same pace that P. I could take this, I could plug it in, I could basically copy this component and plug it in, but it's a little more expensive, a tiny bit more expensive than saying, I have already calculated these transformations. These are the transformations that I want, and with their 4x4 matrices in the backend. So what I can do is I can just say, why don't I just take that transformation and I apply it to a different object. So if I go to utilities and I go to transform, this component takes any geometry and applies a transformation defined by that 4x4 matrix, or as you can see by this object type with the hexagon, which is like the swirly kind of arrow. So what I can do is I can say, let me transform this geometry, the C letter, and let me apply the same transformation that I generated when moving these VREPs here. And what you can see is that that exact same transformation gets applied to this other object. And it doesn't matter that the object is anywhere else, because what this transformation was moving relative to where it was before. So in this case, this works, and it saves us a little bit of computational time. In Grasshopper world, this doesn't really make a difference, but if we were working with code, or if we were doing this for like millions and millions of objects, this would definitely give us an advantage. And at the same time, it gets us closer to understanding how numerically in the real world spatial transformations work. So we're not really going to cover any more in-depth numerical transformations here in this course, in this series, but if you're interested in learning more, I very much welcome you to check out the lecture that I gave on transformation, the lecture that I give every year on spatial transformations in my Introduction to Computational Design course at the Harvard Graduate School of Design, where I go over topics of rotational matrices and how things are represented with 3x3 matrices, and how spatial transformations can be combined together, and how they can be applied to any object, and how they're also super useful for projection transformations and for other topics. Okay, it's a bit more advanced, this lecture, that what I would like for this introductory series, but it's super interesting, I think, nonetheless, if you're really interested in a topic. There will be a link popping up somewhere as a card, or the link will be here on the description of the video. You will be able to find this somehow. So that was spatial transformations in three-dimensional space and how they are handled in Grasshopper. So I think at this point, I think we are ready to take everything we have learned in this section and start applying it with examples, with concrete examples. So I think that's what I'm going to do in the next few videos. In the meantime, if you liked what you saw here, you may want to consider liking this video, subscribing to the channel, and maybe even turning on notifications to get updates on when we go live and when do we post new videos. Thank you very much for watching, and I'll see you on the next videos, which I think are going to be, we're going to do a few hands-on exercises now to practice all this stuff. See you. Bye.